From the dawn of consciousness, humanity has looked to the heavens, a canvas of infinite mystery, and whispered a question that resonates through the deepest corridors of our being. Are we alone for millennia? This was a query for poets, philosophers, and dreamers. But today, we stand at a remarkable threshold. Science, with its ever-sharpening tools and insatiable curiosity, is beginning to sketch the outlines of an answer. Are we, in this very epoch, about to find life far from Earth? The knowledge that thousands of worlds, the so-called exoplanets, orbit stars other than our own sun, is no longer the realm of science fiction. It is established astronomical fact. This realization, burgeoning over the past quarter century, has transformed our cosmic perspective. The grand question in the pale blue dot. The journey from the first tentative detections of these alien worlds, many of them initially appearing hostile, with conditions making life as we know it impossible, to the most recent discoveries of planets that bear a striking, tantalizing similarity to our own Earth, has been one of astonishingly rapid progress. This relentless advancement, achieved in just the last 25 years, fuels a profound and growing conviction within the scientific community that we are getting closer and closer, perhaps with each passing year, to the monumental discovery of an inhabited planet. Yet, the path to such a revelation is anything but simple. Discovering life somewhere within the unfathomable expanse of our galaxy will not be easy. Scientists, with unwavering determination, must confront and overcome major technological challenges, obstacles that test the very limits of human ingenuity and our current understanding of the cosmos. We are separated from other stars, even our nearest stellar neighbors, by gulfs of space so vast they beggar the imagination, distances measured not in miles or kilometers, but in light years, the very distance light itself, the fastest thing in the universe, travels in an entire year. And beyond these almost insurmountable physical barriers, a constellation of fundamental questions still remains unanswered. Questions that strike at the very heart of our quest. How did life, in all its intricate complexity, first ignite on our own planet, this precious, singular oasis of blue and green, in what kinds of diverse, perhaps even extreme, habitats could life appear and subsequently develop elsewhere, adapting and evolving under conditions that might seem utterly alien, perhaps even lethal, to us? Despite these daunting unknowns, astonishing projects, beacons of human ambition and scientific aspiration await us. Consider the James Webb Space Telescope, a marvel of engineering already peering into the depths of space, uniquely capable of studying the delicate atmospheres of distant planets in a direct search for the chemical signs of life. And looking to the near future, there is the ELT, the extremely large telescope, a gigantic ground-based observatory that promises to open an entirely new door, a fresh portal, onto an unknown universe, potentially revealing vistas that will forever alter our perception of reality and our place within it. This, truly, is the time for the dream of a whole generation of astronomers, and indeed, the collective dream of all humankind, to potentially come true. Because in the end, the search for other worlds, for other life, holds the extraordinary potential to provide a reply, perhaps even a definitive answer, to that most fundamental and enduring of all questions are we alone in the universe? To fully grasp the profound context of this search, to feel its emotional weight, we must cast our minds back, or rather, our gaze outward, to a singular, poignant moment in the year 1990. Shortly before abandoning our solar system forever, its primary mission of exploration largely complete, its instruments still faithfully reporting back across the void. The Voyager 1 space probe, a tiny, tenacious emissary of Earth, was commanded to look back one last time. From an almost inconceivable distance of 6,000 million kilometers, a vantage point from which our entire solar system would appear as little more than a collection of faint, insignificant sparks. It captured an image that would resonate through history, an image that would become an icon of the space age. Suspended on a single, delicate ray of sunlight, almost lost in the cosmic glare and the vastness of interplanetary space, the presence of a dim, almost imperceptible point of blue light could just be made out. That was Earth, our home, our world, everything we have ever known. The visionary astronomer Carl Sagan, who had passionately championed this act of cosmic self-reflection, famously called it the pale blue dot. Looking at that image, it is hard not to feel a profound sense of our own fragility, our preciousness, and indeed, our apparent isolation in the grand cosmic theater. And it compels us to ask, is it truly reasonable to think that this tiny, solitary dot, this mote of dust suspended in a sunbeam, is the only inhabited place in the entire, sprawling, almost unimaginably vast universe, as Carl Sagan himself so eloquently articulated? If the Earth is the only place where there is life, then it seems like an awful waste of space. If life, in all its tenacity, its adaptability, and its inherent drive towards complexity, has arisen on a planet such as ours, a world with its specific chemical composition, its particular orbital distance from its star, its unique geological and atmospheric history, then why, by what cosmic decree, could it not have also appeared, through similar processes of cosmic chemistry and Darwinian evolution, on other worlds, perhaps on countless other worlds, scattered like seeds across the galactic winds, each one a potential cradle for life? Just a few short decades ago, when we looked up at the night sky, our perception was limited. We simply saw stars, beautiful, twinkling points of light, certainly, each a distant sun, but essentially just that, individual stars. But today, our understanding, our cosmic imagination, has been irrevocably, wonderfully altered. When we now look at those same stars, those familiar constellations, we can, with solid scientific justification, imagine not just solitary points of light, but thousands upon thousands of planets orbiting them. We can envision a rich, intricate tapestry of planetary systems woven throughout the fabric of our galaxy, a galaxy itself just one among billions. And these planets, we now understand, have been formed in the same fundamental way as our own solar system, coalescing over eons from vast, swirling disks of gas and dust surrounding their nascent, youthful stars, a universal, almost inevitable, process of cosmic creation. To truly begin to grasp the sheer potential for life elsewhere, one must first attempt to confront the staggering, mind-boggling scale of our universe. How many stars are there, just within our own Milky Way galaxy, let alone in the countless other galaxies that speckle the observable cosmos like luminous grains of sand on an infinite shore? The number is, quite frankly, very, very big, a figure that defies easy comprehension and dwarfs any terrestrial analogy. Sometimes, in an attempt to make it relatable, we think that the number of grains of sand on all the beaches and deserts of our entire Earth might be a comparable figure, but it's not. The reality is even more immense. Current astronomical estimates suggest that there are about 10 billion stars in the observable universe. That means, if you could somehow count them one by one, there would be roughly 1,000 times more stars in the heavens than there are individual grains of sand on our entire planet. The sheer statistical weight of this number is almost overwhelming. Equations, signals, and enduring paradoxes. Confronted with such an astronomical number of stars, each a potential sun with its own retinue of orbiting worlds, even if life, and particularly intelligent, communicative life, were an exceedingly rare cosmic accident, a statistical improbability of the highest order, the sheer number of worlds on which it could have arisen remains utterly, profoundly enormous. This fundamental realization was understood with striking clarity by the North American astronomer Frank Drake. As early as 1961, Drake put forward his now famous equation, a conceptual framework designed not so much to yield a precise number, but rather to organize our thinking, to systematically break down the grand question of how many communicative civilizations might exist in our Milky Way galaxy into a series of more manageable, albeit still hugely challenging, probabilistic questions. The Drake equation, elegant in its simplicity, attempts to measure the number of civilizations in our Milky Way capable of, and perhaps interested in, communicating with others. It multiplies together several key factors: the average rate of star formation in our galaxy, the fraction of those stars that have planets, the average number of planets that can potentially support life per star that has planets, the fraction of those potentially habitable planets on which life actually arises, the fraction of life-bearing planets on which intelligent life evolves, the fraction of civilizations with intelligent life that develop technology capable of releasing detectable signs of their existence into space, and finally, the length of time such technologically advanced civilizations might release those detectable signals. It is, in all likelihood, an equation whose precise solution will elude us for a very long time, perhaps forever, because we are, at present, largely unaware of the true values of most of its variables. And each of those variables, each term in that chain of probabilities, itself brings up a cascade of new, complex, and fascinating questions, each one a vibrant line of research in current astronomy and astrobiology. As one scientist deeply involved in this multifaceted research has noted, I think what is interesting is it depends on how many stars are in the universe and how many new stars form every year, how many planets they typically have, if they have any planets, how many of those planets are truly habitable. If they are habitable, do they already have life, or perhaps did life arise and then disappear? Do they have intelligent life? Is this intelligent life anything like ours? Will they communicate as we do, or in ways we can't even imagine? Each of these questions, as mentioned, represents a significant and active line of research in contemporary astronomy. We don't yet know with certainty how many stars form in the universe, at what precise rate, for example. So, imagine, if even these fundamental astronomical parameters are still subjects of ongoing investigation, how could we possibly perform the full Drake calculation with any high degree of confidence in the final result? Yet, the spirit of the Drake equation, its powerful impetus to systematically explore the probabilities and to identify the key unknowns, continues to inspire and to guide the search. And so, since the 1970s, driven by the conviction, or at least by the fervent hope, of the existence of other intelligent civilizations within our galaxy, the SETI projects, the search for extraterrestrial intelligence, have diligently, patiently trolled the stars. These projects have employed powerful radio telescopes to listen intently, scanning the cosmic airwaves, sifting through the natural background noise of the universe in search of any faint, artificial signals, any whispers that might betray an extraterrestrial, technological origin. We are, of course, designing these searches based primarily on what we ourselves do, on our own current technological footprint. Here on Earth, we communicate over vast distances, predominantly using radio waves, and indeed, from our current perspective, this remains the most practical and detectable way for signals from a human-like civilization to be perceived from outer space. Over the recent decades of this patient, often thankless, listening, some hopeful, tantalizing signs have occasionally been found, fleeting, unexplained anomalies in the cosmic static that briefly raise pulses and ignite speculation. But alas, upon closer scrutiny and further investigation, none of them have ultimately turned out to be a verifiable greeting from the vastness of interstellar space. One must then ask, were the pioneers of the SETI search, in their early, unbridled enthusiasm, perhaps a shade too optimistic? Did they underestimate the profound silence of the universe, or the sheer, daunting difficulty of the task they had set for themselves? Perhaps a profound shift in our very understanding of the universe's scale, a pivotal astronomical discovery that occurred decades before the first formal SETI projects even began, contributed both to the initial optimism and, subsequently, to a more sober, more measured realization of the immense challenge involved. In the year 1924, the American astronomer Edwin Hubble, through meticulous observation, using the powerful telescopes of his era, and groundbreaking analytical insight, confirmed a revolutionary idea. He demonstrated conclusively that the Andromeda Nebula, long thought by many to be a swirling cloud of gas and dust located within the confines of our own Milky Way galaxy, was in fact not a nebula at all. It was an entirely separate galaxy, a vast, majestic island universe in its own right, containing billions of its own stars, and lying millions of light years beyond the outermost fringes of our own galactic home. In that singular moment of discovery, the universe, as humanity understood it, had suddenly, dramatically, become effectively infinite, or at least vastly, unimaginably larger than anyone had previously dared to conceive. Until that pivotal discovery, scarcely a century ago, almost everybody, scientist and layperson alike, generally thought that our galaxy, The Milky Way was the universe, the entirety of creation, the sum total of all that existed. Now, we know that those little, fuzzy, indistinct dots that appear like faint, ethereal stars through our most powerful telescopes are, in reality, other galaxies, each a colossal stellar system, each containing its own billions, perhaps even trillions of stars. Our perspective has changed so profoundly, so rapidly, that our minds, our everyday intuitions, often struggle to truly comprehend the idea of such immensity, such near infinity. We can certainly manipulate the concept mathematically. We can write down the equations that describe it. But our brains, which evolved on the savannas of Africa to deal with more immediate, more terrestrial concerns like finding food and avoiding predators, did not evolve to intuitively understand this kind of mind-bending cosmic scale. Then, the universe is effectively infinite, or at least so unimaginably vast and sprawling, and is teeming with galaxies, each of which contains thousands of millions, or even billions of stars. It seems almost logical, almost inescapable, to think that other intelligent civilizations, perhaps many like our own, or perhaps wildly different, must surely exist out there somewhere. Why then, given this apparent logical imperative, this statistical probability, have we not yet had any definitive news, any unambiguous signal, any clear indication of contact from any of our potential galactic neighbors? This is the very crux of the profound and unsettling question that the brilliant Italian-American physicist Enrico Fermi is said to have famously, almost casually, posed during a lunchtime conversation with colleagues at Los Alamos in 1950. A question now enshrined in the annals of scientific thought as the Fermi Paradox, where are they? The implication of Fermi's simple yet profound question is clear and deeply challenging given the immense age and staggering size of the universe, and the presumed likelihood of life arising given enough suitable worlds and enough time. We should, by now, have seen or detected some incontrovertible evidence, some clear signals of an alien civilization. Yet, despite decades of looking and listening, we haven't. There are, of course, numerous possible, and often quite unsettling, reasons for this apparent great silence, one stark, and to some, chilling. Possibility is that there simply aren't any other civilizations in our galaxy capable of, or perhaps interested in, communicating. Perhaps we are truly, profoundly alone, at least in this particular cosmic neighborhood, at this particular moment in cosmic time. Another, perhaps more nuanced, possibility is that we are not in the same space and time frame. Civilizations may rise and fall like ephemeral mayflies on a vast cosmic timescale, their windows of technological capability and interstellar communication too brief, too fleeting, to overlap with our own relatively recent emergence as a signal-producing species. Life, as we understand its history on Earth, arose on our planet over 3,500 million years ago, a slow, painstaking, and often precarious evolutionary journey from simple microbes to the complex biosphere we see today. Yet, we, as a species capable of deliberately broadcasting our presence into the vastness of space through radio waves, have only been giving off potentially detectable signals for a mere 100 years or so, an infinitesimal blink of an eye, in the grand sweep of cosmic time. What, then, are the realistic possibilities of our brief period of detectability coinciding with that of another civilization, somewhere else in our vast galaxy, especially when separated by immense gulfs of both space and time? And if we add to this temporal difficulty the almost incomprehensible distances that separate us from even the nearest other worlds that might harbor life, the challenges become even more profoundly complicated. As one astronomer involved in these contemplative calculations explained, if we have a civilization that is, say, 20,000 light years away, even if we were to detect their signal today, it would take a full 20,000 years for our reply, traveling at the speed of light to reach them. And then, if they were to answer back immediately, it would be another 20,000 years for their response to traverse the interstellar void and arrive back at Earth. So, that's a 40,000-year round trip for a single exchange of messages. This is not really a very productive or practical dialogue that we could realistically have. Our galaxy, the Milky Way, is roughly 100,000 light years in dimension, from one spiral arm to the far-flung other. That's a truly huge place, an almost unimaginably vast arena, and the fundamental speed limit of light, as dictated by Einstein's theories, imposes an absolute constraint on any attempt at interstellar conversation or rapid travel. The question, therefore, remains suspended in the cosmic ether, poignant, tantalizing, and profoundly unanswered. Do we really know, with any certainty, whether there's another civilization out there? Maybe there has been, long ago. Their magnificent empires now crumbled to dust, their guiding lights now faded into the long night, their signals long since passed us by, unheard and unrecorded. Maybe there will be, far in the distant future, long after our own sun has exhausted its nuclear fires and our own civilization, perhaps, is no more. Or maybe, just maybe, there is intelligent life out there right now, coexisting with us in this vast galactic ecosystem, but they are too far away for their faint whispers to reach us, or perhaps too different in their nature or their technology for us to recognize their signals. Or maybe they are simply too quiet, content in their own cosmic solitude, for us to perceive their presence. For the time being, despite all our sophisticated searching and all our intricate theories, we just don't know. We do not know if we are alone or not. But even in this profound state of unknowing, even as we grapple with these immense cosmic uncertainties and the weight of these philosophical questions, we have, in the process of our search, discovered so many other amazing, breathtaking things about the universe itself, its intricate structure, its violent and beautiful history, the elegant physical laws that govern its operation, from the smallest subatomic particle to the grandest supercluster of galaxies. And it is this intrinsic journey of discovery, this relentless, curiosity-driven pursuit of knowledge that continues to propel us forward as we delve ever deeper into the sophisticated methods and the landmark milestones that are, step by painstaking step, bringing us ever closer to a potential answer, an answer that could, in a single moment, change everything we thought we knew about ourselves and our place in the cosmos. The quest for understanding is, in itself, a profound testament to the very life we seek to find elsewhere, inquisitive, persistent, and forever reaching for the distant stars. The Astronomer's Toolkit, Deciphering Cosmic Light. Welcome back to our ongoing exploration of the universe and our search for companionship among the stars, in our profound quest to find life beyond the familiar confines of Earth, to seek an answer to that age-old, resonant question of whether we are solitary beings adrift in an immense cosmic ocean or part of a vast, interconnected web of existence. The very first, indispensable step is the discovery and characterization of other worlds. Before we can even begin to dream of detecting the subtle chemical signatures of life, or to contemplate the almost unimaginable implications of potential contact, we must first locate these distant celestial bodies, these exoplanets, faithfully orbiting stars far beyond our own familiar sun. But how? One might reasonably wonder. Do astronomers manage to study these remote objects that are light years away, often utterly invisible to the unassisted human eye, and forever beyond our current physical reach? The field of astronomy, particularly when it ventures into the challenging realm of extrasolar planets, inherently involves a major, almost defining difficulty we cannot, as scientists in many other disciplines routinely might, bring our subject of study, a distant star, a swirling nebula, or an elusive exoplanet, into the controlled environment of the laboratory for meticulous, hands-on examination. Often, we cannot even directly see the specific object of our intense scientific scrutiny, especially when that object is a small, dim planet, lost in the overwhelming glare of its parent star. How then, given these profound and inherent limitations, has it been possible for humanity to accumulate such a vast, intricate, and ever-expanding body of knowledge about the cosmos and its myriad, diverse inhabitants? The key, the fundamental secret to unlocking the universe's deepest mysteries from such immense distances, lies in patient, meticulous, and often incredibly ingenious observation. It relies on making clever and insightful use of the opportunities that the universe itself, governed by its immutable and universally applicable physical laws, graciously, if sometimes cryptically, offers us. Every single object in the universe, from the smallest, almost infinitesimal dust grain drifting in the interstellar void, to the most massive, incandescent star blazing in the galactic core, from a still-forming, nascent planet coalescing in a protoplanetary disk to an entire, majestic galaxy containing billions of stars, emits energy. This energy, the universe's silent language, very often takes the form of electromagnetic radiation. This is a broad, continuous spectrum of waves that encompasses everything from the long, gentle undulations of radio waves and microwaves, through the warmth of infrared radiation and the familiar colors of visible light, to the energetic, high-frequency realms of ultraviolet light, X-rays, and the intensely powerful gamma rays. The specific characteristics of this emitted radiation, its overall intensity, its distribution across the different wavelengths of the spectrum, the presence of specific bright emission lines or dark absorption lines, depend critically and informatively on the temperature, the chemical composition, the density, and the physical state of the emitting object. Light, in its most fundamental physical sense, is a form of energy and one of the most powerful and versatile astronomical methods ever devised. A technique known as spectroscopy allows us to dissect this incoming cosmic energy with remarkable precision. Using specialized devices like diffraction gratings or prisms, coupled with sophisticated detectors and instruments, spectroscopy can split the faint, ancient light arriving from a distant celestial body into its individual portions, its constituent wavelengths or colors, much like a simple prism famously creates a rainbow from sunlight by dispersing its different wavelengths. And this collection of dispersed light, this unique, characteristic fingerprint of brightness versus wavelength, we call a spectrum. We humans, with our biologically evolved eyes, can only perceive a very tiny, almost insignificant sliver of this vast electromagnetic spectrum, the narrow band of wavelengths we call visible light. But the universe, in its full, magnificent glory, reveals its deepest secrets to us across the entire breadth of the electromagnetic spectrum, a vast, rich canvas of information patiently waiting to be deciphered by our instruments and our intellect. As one expert in the intricate field of astrophysical instrumentation explains, a spectrum that we can see with our own eyes, the familiar rainbow, is just a very, very tiny part of the possible range of wavelengths that are emitted by all the different kinds of objects in the universe. So, of course, different objects emit differently. Some of them, like cool dust clouds or young planets, emit most of their radiation in the infrared part of the spectrum. Hotter objects, like stars, might peak in the optical or even the ultraviolet. Extremely energetic phenomena, like accretion disks around black holes or supernova remnants, can blaze in X-rays or gamma rays. And analyzing these spectra, understanding these different emissions, tells us what are the inner makings of stars and planets, what is the detailed structure of galaxies, and indeed, what is the overall architecture and evolution of the universe on its largest scales. This remarkable ability to read the light, to decode its subtle messages imprinted by atoms and molecules light years away, is the absolute cornerstone of modern astrophysics. It allows us to determine the surface temperature of a distant star with surprising accuracy, to identify the specific chemical elements present in its atmosphere, to measure its precise speed towards or away from us using the Doppler effect, and even indirectly but powerfully, to infer the presence and properties of unseen companions, such as exoplanets, orbiting around it. But to capture this incredibly faint, unimaginably ancient light that has often traveled for thousands, millions, or even billions of years across the desolate vacuum of space to finally reach our telescopes, astronomy not only requires these highly sophisticated instruments capable of looking further and with greater analytical power than the unaided naked eye, it also, critically and fundamentally, needs specific places on Earth that are blessed with exceptionally good, pristine conditions for astronomical observation. These are typically remote, often inhospitable, high-altitude locations, deliberately situated far from the pervasive glow of artificial light, pollution emanating from our cities and towns, places where the overlying atmosphere is as thin, as stable, and as transparent as possible. And, of course, it requires telescopes, great, modern temples of science, marvels of engineering, capable of gathering vast amounts of this precious cosmic light, collecting the individual photons that are the fundamental messengers from the distant universe. One of the most impressive and productive of these modern ground-based observatories is the Gran Telescopio Canarias, often referred to by its acronym GTC. This magnificent instrument is perched high atop an extinct volcano on the island of La Palma, one of Spain's Canary Islands, floating in the Atlantic Ocean off the coast of Africa. Romano Corradi, the director of the GTC, elaborates on the essential, almost non-negotiable, requirements for such a world-class astronomical facility. We astronomers, we absolutely need that there are no clouds, or as few as possible. And here on the mountains of La Palma, for about 75% of the time, there are no clouds. That's a very high fraction of usable nights. Also, there are two other very important things we have here. We have the benefit of the trade winds, which are very good because they create a very stable, laminar flow of air over the mountaintop, meaning the atmosphere is very clean and the turbulence is minimized. This allows us to take very sharp, clear images of the universe, and, crucially, we are on a relatively small island, which is protected by law against excessive light pollution, helping to keep our night skies dark. Here, amidst the stark, almost lunar beauty of the volcanic landscape, under some of the clearest and darkest night skies on the entire planet, astronomers engage in their nightly vigil, a patient and meticulous dance with the cosmos. Their primary task, as Director Corradi succinctly puts it, is to collect the light that comes from the stars and other celestial objects, and then to either get images of those objects or, more often, to analyze that light in detail using our various instruments. To achieve this, they employ a diverse and sophisticated array of scientific instruments, some of which are designed to see the kind of light that our human eyes can perceive, the optical spectrum, while other, equally important, instruments are able to detect light that our eyes are completely blind to, such as the longer wavelengths of infrared light. Infrared astronomy is particularly crucial because it can reveal cooler objects like forming stars and planets, or allow us to peer through vast, obscuring clouds of interstellar dust that are opaque to visible light. The enormous primary mirrors of these large telescopes, which are not made of a single piece of glass, but are typically composed of many smaller, precisely shaped, hexagonal segments fitted together like a giant mosaic, act as colossal light buckets. They allow astronomers to gather the incredibly dim, almost ghostly particles of light, the individual photons, that finally reach us after their unimaginably long journeys of thousands, millions, or even billions of years, carrying with them faint, ancient tales from distant stars, nebulae, and even more distant galaxies, relics from the universe's deep past. The Gran Telescopio Canarias, the GTC, is currently the largest single-aperture optical telescope in the world. Its segmented primary mirror, a marvel of optomechanical engineering, has a collective light-gathering diameter equivalent to a colossal 10 meters. This immense light-gathering power, this ability to collect as many photons as possible, is absolutely crucial for many cutting-edge areas of modern astronomy. But it is especially vital for the incredibly challenging hunt for exoplanets, which are often vanishingly faint compared to the overwhelming glare of their host stars. and for studying their even fainter atmospheric signatures. It's worth noting, as an interesting technical detail, that these giant modern telescopes don't use massive lenses, like smaller, amateur telescopes or traditional spyglasses might. It's far easier, both mechanically and optically, to build, support, and maintain the precise shape of extremely large mirrors than it would be to create equally massive, perfectly formed, and optically flawless lenses. The profound idea that there might be other worlds beyond the familiar confines of our own solar system, planets orbiting other suns, is not, in itself, a particularly new or modern one. Down through the centuries, from antiquity through the Renaissance and beyond, great thinkers, insightful philosophers, and imaginative writers, figures such as Epicurus in ancient Greece, or the tragically fated Renaissance scholar Giordano Bruno, hazarded the well-reasoned opinion, based on philosophical analogy and a belief in the uniformity of nature, that there simply must be planets orbiting other stars. It was a beautiful, intellectually compelling, and deeply resonant idea, but for a very, very long time, it remained purely in the realm of abstract speculation, a fascinating concept far beyond the reach of any possible empirical verification or scientific proof. It was not, however, until the relatively recent past, specifically the 1990s, that the relentless, accelerating development of technology, particularly the advent of highly sensitive electronic light detectors like CCDs, the precision engineering of spectrographs, and the rapidly increasing power of computers for data analysis, finally allowed for the actual, unambiguous detection of these long-suspected extrasolar planets. It serves as a stark and humbling reminder of just how rapidly our scientific capabilities have advanced in a very short span of human history until just a couple of decades ago. The 8 recognized planets of our own solar system were the only planets whose existence we knew with absolute certainty in the entire vast universe. The fundamental question that occupies so many thoughtful minds, the profound inquiry concerning the ultimate origin of life itself and, by extension, whether that precious spark of existence has ignited elsewhere in the cosmos, hinges critically and inescapably on this first crucial step, the detection of other potential abodes for life. Before you can even begin to contemplate the possibility of extraterrestrial life, the very first thing you need to have, the foundational requirement, is a place where life can plausibly exist. We astronomers, or at least a significant number of us, had always suspected, based on our understanding of stellar and planetary formation theories, that there should be other planets out there. Indeed, from a purely theoretical point of view, the formation of planets looked like a natural, almost inevitable, byproduct of the complex physical processes involved in the birth of stars themselves, from collapsing clouds of interstellar gas and dust. The historic and picturesque city of Geneva, Switzerland, renowned globally for its long tradition of precision watchmaking and its prominent role in international diplomacy and finance, was, perhaps somewhat unexpectedly, to become the setting for this first successful, scientifically validated search for worlds beyond our solar system. In the early to mid-1990s, several highly skilled and intensely competitive research teams around the globe were deeply involved in this exhilarating, high-stakes scientific race, each team pushing the absolute limits of their sophisticated instruments and their intricate analytical techniques, the first to definitively cross the finish line, the team to proudly announce the first confirmed detection of a planet orbiting a sun-like star outside of our solar system was the distinguished group led by the Swiss astronomers Didier Queloz and Michel Maillot. In the landmark year of 1995, the world of science, and indeed the wider world, was formally introduced to a new celestial citizen, the exoplanet designated 51 Pegasi b. It was a truly watershed moment in the history of astronomy, a discovery that would forever and irrevocably change our human view of the cosmos and our potential place within it. This monumental achievement would, many years later, deservedly earn its discoverers, Mayer and Queloz, the Nobel Prize in Physics. Didier Queloz, reflecting on that pivotal and exhilarating time in his scientific career, remarked with characteristic modesty and insight, "We had just got to know 51 Pegasi b. We just arrived at the right time, a moment in history where the available technology, the precision of our instruments, finally allowed us to give a genuine scientific answer, a data-driven response to this very old, very profound philosophical question. So, I feel myself very fortunate, very happy, to have just arrived at this good moment in scientific history in order to be part of the team that discovered the first exoplanet around a sun-like star." The ingenious and highly sensitive method that Michel Mayer and Didier Queloz had so successfully and groundbreakingly employed is known to astronomers as the radial velocity technique. It is sometimes more colloquially, and perhaps more intuitively, referred to as the Wobble method. By meticulously applying this technique, they were able to detect the incredibly slight, yet periodic, movements of the star 51. Pegasi, subtle shifts in its position that were being caused by the persistent gravitational tug of an unseen, orbiting planetary companion, as an exoplanet circles its host star, its own gravity, though much weaker than the stars, inexorably causes the star to move in a tiny corresponding orbit of its own. It's a delicate, gravitational dance performed by the star and its planet around their common center of mass, a point often located very close to, or even within, the star itself if the planet is much less massive. When we, as observers on Earth, carefully measure the radial velocity of distant stars, that is, their speed directly along our line of sight, either towards us or away from us, it's all about our instrumental ability to measure these very, very tiny, almost infinitesimal variations in that stellar velocity over time. This small periodic stellar movement, this subtle wobble, can be precisely measured because the waves of light in the spectrum emitted by the star systematically vary due to the well-understood physical principle known as the Doppler effect. This is exactly the same effect that causes the noticeable change in pitch of an ambulance siren as it speeds past you as the ambulance moves towards you. The sound waves it emits are compressed, leading to a shorter wavelength and thus a higher perceived pitch. Conversely, as it moves away from you, the sound waves are stretched out, resulting in a longer wavelength and a lower perceived pitch. Similarly, as a star, influenced by an orbiting planet, wobbles slightly towards us in its tiny orbit, the light waves it emits are minutely compressed, causing its entire spectrum to shift very slightly towards the blue end of the rainbow. And as it wobbles away from us, its light waves are correspondingly stretched, shifting its spectrum towards the red end. The star itself might be majestically careening through the vastness of the galaxy at truly enormous speeds, perhaps hundreds of thousands of kilometers per hour relative to our solar system. However, the incredibly subtle effect that astronomers are attempting to measure, the tiny periodic wobble induced by an orbiting planet, is often at the level of mere meters per second in velocity, or even less. To put this extraordinary challenge into a more familiar perspective, consider the gravitational pull of Jupiter, by far the largest and most massive planet in our own solar system. Jupiter's presence causes our Sun to wobble at a speed of approximately 12 meters per second, a speed roughly equivalent to a fast human sprint. The first generation of highly specialized astronomical instruments, such as the LOD spectrograph used by Mayer and Queloz at the Haute-Provence Observatory in France, were just sensitive enough, just precise enough, to reliably get to that level of detection capability. And so, it was entirely natural, and indeed expected, that the very first exoplanets they successfully detected using this pioneering technique were predominantly big, massive planets, gas giants comparable in size or mass to Jupiter, orbiting relatively close to their host stars, as these would produce the largest and most easily discernible stellar wobbles. New windows on worlds, transits, images, and the red frontier. Welcome back. The era of exoplanet discovery, ignited by the detection of 51 Pegasi b and its hot Jupiter brethren, was in full swing. The radial velocity method had proven its power, but the universe, it seemed, had an even greater diversity of worlds to reveal, and scientists were eager for new techniques to uncover them, especially those smaller, potentially rockier planets that might offer more clement conditions for life. While the teams perfecting the radial velocity technique continued their meticulous work, other astronomers were pursuing a different path, one that relied not on a star's wobble, but on its wink. This was the transit method, and Hans Dieg was among its early proponents, recalling his entry into this nascent field. In 1994, I was approached by a colleague, Lawrence Doyle, who proposed an experiment to search for exoplanets. So we started the first observational search for exoplanets with the method of transits. This elegant technique is based on the study of minuscule changes in a star's brightness. One doesn't observe the planet directly. Instead, the focus is on the star's light. If a planet's orbit happens to be aligned edge-on from our perspective on Earth, it will periodically pass in front of its star, an event astronomers call a transit. During these few hours, the planet will block a tiny fraction of the starlight, causing the star to appear slightly fainter. To confirm a planet, this dimming must be periodic, repeating reliably, and at least 3 such events are typically required to rule out other stellar phenomena. The primary limitation, however, is this precise geometric alignment. Only a small fraction of planetary systems will be oriented in just the right way for us to observe transits. Thus, the strategy has always been to observe many stars simultaneously, thousands, even hundreds of thousands, hoping that chance will align a few of them perfectly. While Dieg's early efforts were pioneering, the transit method truly came into its own with the launch of NASA's Kepler Space Telescope in 2009. Kepler was a dedicated planet-hunting observatory, staring unblinkingly at a single patch of sky for years, monitoring the brightness of over 150,000 stars with unprecedented precision. Kepler revolutionized the search, confirming hundreds of new exoplanets and identifying thousands of candidates. It made planetary transits the most successful detection method to date, revealing the first systems with multiple planets transiting the same star and amplifying enormously the sheer variety of planetary systems known to exist. It found many unusual things, truly a true revolution in our understanding of extrasolar planets. A few years before Kepler's launch, in 2003, another significant advancement occurred with the installation of HARPS, the High Accuracy Radial Velocity Planet Searcher, an instrument of exceptional stability and precision, capable of detecting stellar movements as slight as 1 meter per second. HARPS, while still far from the 9 centimeters per second wobble Earth induces in our Sun, opened the door to discovering smaller and smaller planets. As astronomers using HARPS discovered, if you look in our solar system, there is nothing between planets like the Earth and planets like Uranus or Neptune. But in all or most of the other solar systems, there are what we call super-Earths or mini-Neptunes, meaning planets that are probably mainly rocky, but with masses between 2 and 10 times the mass of the Earth. These worlds, unknown in our solar system, appear to be ubiquitous in the universe. Then, in 2004, a new name appeared to mark a historic moment, 2M1207b, the first extrasolar planet to be directly imaged. Capturing a direct visual of an exoplanet is incredibly difficult. Planets are not very bright objects, and their host stars are overwhelmingly brilliant. The challenge is akin to trying to spot a tiny firefly perched on the bulb of a blindingly bright lighthouse from a distance of about 5,000 kilometers. To even attempt this, astronomers must develop specific techniques and instruments to remove or suppress the star's light, allowing the faint image of the planet to emerge. Furthermore, Earth's turbulent atmosphere distorts incoming starlight, blurring an already faint image. To overcome this, a complex technique known as adaptive optics is employed. This is a control system where sensors detect the optical distortions from the atmosphere as they occur, and this information is then fed back in real time to a deformable mirror, which adjusts its shape about 1,000 times a second to correct for these disturbances, producing a much sharper image. The advantage of a direct image is the wealth of information it can provide: the planet's size, the composition of its atmosphere, details of its orbit, and its temperature. The disadvantage is that, currently, we can only obtain direct images of young, still warm planets, or those which are a very long way from their star, where the contrast issue is less severe. For most exoplanets, we must continue to rely on indirect methods like radial velocity, which gives us the planet's minimum mass, or the transit method, from which we can ascertain its size. If we are fortunate enough to have both measurements for the same planet, we can compute its mean density, which tells us a lot about whether it is primarily rocky, like Earth, or gaseous, like Jupiter. Combining transit and radial velocity data is therefore key to truly getting to know the fundamental characteristics of a planet, although this is not always possible. Proxima b, the nearest known exoplanet, was detected using the radial velocity method. However, as its orbit is not aligned with Earth for us to observe a transit, we have not yet been able to determine its size. Chance has a significant role to play in transit detections. With radial velocity, on the other hand, success is virtually assured, provided the planet is not at too great a distance from us and is massive enough to produce a detectable signal. For this reason, New search projects are increasingly concentrating on the stars closest to our Sun. In this solar vicinity, we are seeing that the frequency, the occurrence rate of planets, is very large. At least 50% of these nearby stars have planets, and this includes even small ones. If we extrapolate this a bit, it means that, on average, one star out of every 2 in the galaxy likely has at least one planet. Considering there are hundreds of billions of stars in our galaxy, this implies there are at least hundreds of billions of planets, a truly staggering number of potential abodes for life. Not all solar systems, however, are ideal for life as we currently understand it. A wide diversity of stars exists, classified mainly by their temperature and mass. If we have to choose a good place to live, it is probably best to avoid the hottest and most massive stars in the universe. These celestial behemoths have extremely short lifetimes, often consuming their nuclear fuel and dying violently in a supernova explosion within just a few million years. The higher mass stars are much less likely to form stable planets, and even if they do, their brief and tumultuous existence hardly provides the eons of stability thought necessary for life to arise and evolve. In contrast, yellow dwarfs such as our Sun, which are G-type stars, fuse hydrogen much more slowly, enjoying lifespans of around 10,000 million years. This vast timescale would, in theory, allow ample opportunity for life to develop. Originally, astronomers were primarily trying to look for exoplanets around these G-type stars, because our Sun is a G-type star, and, of course, what you really always want to find is an Earth around a star which is very similar to the Sun. In principle, what we are after is a twin of ourself. Yellow dwarfs such as our Sun certainly provide suitable conditions for the development of life, but finding a true twin planet like the Earth orbiting one of them, a planet that is both small in size and situated at just the right distance from its star, is, for the moment, a very difficult task. We have found planets very close to their stars, and planets relatively far away from their stars, because in those situations, the overwhelming light of the star is not bothering us so much, or the planetary signal is easier to disentangle. But it just so happens, through a quirk of observational physics, that an Earth-like planet, which is at just the right distance from its star, so it's not too hot nor too cold, are the most difficult to find. It's bad luck, observationally speaking, but that's physics. Since the first detections and the continuous improvement of our instrumentation, astronomers have been relentlessly trying to get to these small planets at a good distance from their star, where liquid water could potentially exist at the surface of the planet. That's what we call habitable, in a very naive but operationally useful way. We do not yet know precisely how life first came about on Earth, but we do know that it would have been impossible without the presence of liquid water. The search for another Earth is therefore inextricably conditioned by the presence of water, specifically liquid water, within what astronomers call the habitable zone. The habitable zone is a concept that is in constant redefinition, and its extent depends on several different factors: how much light the host star emits, the wavelength distribution of this light, the surface gravity of the planet, the specific components of that atmosphere, and also the sheer abundance of water on the planet. A planet situated within this calculated habitable zone could still have a surface temperature very different from what might be naively expected, depending on whether it absorbs or reflects the radiation from its star. A very important factor here is the presence of an atmosphere. The mean surface temperature on the Earth is about 15 degrees Celsius, but it is estimated that if there were no atmosphere, if Earth were a bare rock, its average temperature would drop to about minus 20 degrees Celsius. This crucial increase in temperature is produced by the greenhouse effect. An extreme example of this is the planet Venus, where runaway greenhouse gases have formed such a dense atmosphere that the surface pressure is 90 times that of Earth. It is for this reason that its surface temperature has increased by over 500 degrees Celsius, making it hotter than Mercury. On the other hand, there's a property called albedo, which describes what fraction of the incoming starlight is reflected by the surface of the planet. This depends on the composition of the planet and also in which state these components are. This delicate equilibrium between the warming greenhouse effect and the cooling influence of albedo finally determines what the mean temperature of the surface is. Temperature, however, is not the only condition for a planet to have liquid water. The pressure on its surface must also be taken into account. Planets that are too large will probably have an important, massive atmosphere. And if the atmosphere is too massive, the pressure at the surface will not allow water to be liquid. Conversely, if the planet is too small, it might not be massive enough to retain its atmosphere, which could gradually evaporate into space. This is the case with Mars, which has a very light atmosphere. Although during the Martian day its temperature can be pleasant, around 20 degrees Celsius, the pressure is so light that if water existed on its surface, it would change directly from ice to vapor. So, we need to find planets that have a size approximately between that of Mars and 1.5 times that of the Earth. It is believed that in this mass range, planets have the best possibility of retaining liquid water at their surface. Thousands of millions of years ago, Mars was very similar to our planet. Perhaps it once held life, and below its surface, this life may still exist. Today, we know that some regions of the Earth that were once considered sterile actually contain extremophilic microorganisms capable of living under extreme conditions of temperature, pressure, or acidity. It seems that life is highly adaptable, very tenacious, and even in extreme sites, we find bits of it, a few species hanging on or well adapted to those environments. Are the limits to life much wider than we imagine? If this were the case, our possibilities of finding it would surely increase. 20 years ago, we didn't even know how to find one planet. Now we have found thousands. Now, we will be finding Earth-like planets as well, and then we can start looking to see if they are really habitable, and if there is life on them or not. Finding a small, rocky planet like the Earth is, as we've seen, easier if it's near its star. On the other hand, if we want to find life, it is essential for the planet to be in its habitable zone. To ensure that these two requirements, detectability and potential habitability, are met, astronomers must increasingly search for a type of star that is smaller and colder than our Sun, the red dwarfs. Anytime you go outside on starry nights and look at the sky, none of the stars that you are seeing with your naked eye is a red dwarf. They are so faint that none of them can be seen without a telescope, and still, they outnumber the stars that you are seeing. Red dwarfs are the most abundant stars in our galaxy. A remarkable 70% of all stars in our galaxy are red dwarfs. And they are very interesting because, with our current techniques and instrumentation, we can learn more things about their planets, and we have a realistic hope of not only detecting the planet, but also looking at what the atmosphere of those planets are made of. They are considered the most suitable candidates to be explored for the presence of life. Red dwarfs also have another crucial advantage: their incredible longevity. Red dwarfs burn their nuclear fuels very, very slowly. So when they sit on the main sequence, which is where stars steadily burn hydrogen in their cores, red dwarfs can be there for the whole of the age of the universe, and much longer. Life, if it arises, has literally all the time in the world to develop. In recent years, planets similar in size to the Earth have indeed been found orbiting within the habitable zones of red dwarf stars. Could any of them provide conditions genuinely suitable for life? This kind of planet is easier to detect, and today we have several candidate planets in the habitable zones of these stars. But we have to keep in mind that these planets, to be warm enough, are so close to their small star that maybe this is not really the better condition for life development. Red dwarfs are much more active than our Sun and could potentially finish off the atmosphere of a nearby planet in a few million years with powerful flares, without giving life time to develop. Moreover, as they are so close to each other, the gravity of the star often captures the rotation of the planet, so that the latter always shows the same face to the star, tidal locking. This causes huge differences in temperature between the hemisphere that receives light and the one in perpetual shade. With such a gloomy outlook, one might ask if planets could develop mechanisms to favor the emergence of life. Further studies and more advanced observations could give us the answer. For centuries, human beings have tried to know if we are alone in the universe or not. At the moment, we have, for the first time probably in our history, started a very challenged program that will dedicate many, many nights on 4-meter class telescopes to make the first survey of Earth-like planets around these red dwarfs. Who knows if maybe in some centuries or so, this survey could be used as a roadmap to go to other places, because in the end, what we are searching for are similar homes to our own. An instrument crucial for implementing this project is Carmenes, which has been installed in the largest telescope in mainland Europe. Jesus Aceituno and his team are searching for planets like the Earth around red dwarf stars. They select a sample of about 300 stars and are monitoring those stars almost every night. What is really new in Carmenes is that it observes simultaneously from the very blue wavelengths all the way until the infrared ones. And this is what converts Carmenes into something really unique in the world. Observation over this wide range helps to differentiate the signal of a planet from that which the activity of a star generates. In addition, Carmenes will also allow scientists to find out the composition of the atmospheres of these planets. With Carmenes, they have the technology to know the chemical composition of the atmosphere, which is also the second important part, just to be sure there could actually exist life on the surface of the planet. Atmospheric whispers, giant eyes, and the enduring dream. The study of the components of atmospheres on distant planets is a major challenge, a frontier in which we are still taking the very first tentative steps. Right now, we have discovered thousands of these exoplanets. Now, we would like to characterize them. We would like to know more about them than just the fact that they exist. There is a lot of experimental work being built, a lot of sophisticated instruments being developed, all with the aim of trying to access these precious atmospheric data. It's not easy. It's actually much easier to detect a planet now, although it wasn't easy at all at the very beginning. but now we generally know how to do it. So detection is no longer the primary problem for many types of planets. But it's much more difficult to go now and actually measure things at the surface, or more realistically, in the atmosphere of these distant worlds. And the only thing we can really measure from so far away, across light years of intervening space, is the planet's atmosphere. We are now in the era of detecting potentially habitable planets, particularly around these small red dwarf stars. But in doing so, we are also diligently preparing for the real, ultimate detection of other Earths, meaning Earth-type planets orbiting stars very much like our Sun. And that capability astronomers anticipate will likely come within the next 10 to 15 years. And hopefully, by then, we will also have the new, even more powerful facilities needed to then effectively characterize their atmospheres. Because that's another enormous challenge, perhaps the greatest of them all. Discoveries such as the remarkable TRAPPIST-1 system, a nearby ultra-cool dwarf star orbited by 7 Earth-sized planets, several of which lie within its habitable zone, and all of which transit their star as seen from Earth, provide excellent, almost tailor-made opportunities for studying atmospheres. When there is a transit, the planet passes directly in between its star and us, the observers. So, some of the starlight will filter through the upper layers of the planet's atmosphere, if it possesses one, before that light continues its journey to our telescopes and detectors. Consequently, superimposed upon the light spectrum of the star, there will be a faint, subtle imprint, a spectral signature, of the chemical composition of the planet's atmosphere. If you can accurately measure this tiny variation in starlight at different wavelengths, a technique known as transmission spectroscopy, you have a direct method to access information about the atmospheric constituents and potentially even find traces of life. How, then, can we identify these elusive traces of life, these biosignatures, from such immense distances which specific elements, or more likely, combinations of elements, present in a distant planet's atmosphere must appear for us to even begin to suppose, with any degree of scientific confidence, that they are inhabited, if a hypothetical alien observer were looking at our own planet, Earth, from a very far away vantage point, and possessed the sophisticated technology to analyze our atmosphere, they would be able to see certain distinct atmospheric signals. They would certainly detect the presence of abundant water vapor. They would also see significant quantities of oxygen, a highly reactive gas that, on Earth, is overwhelmingly produced by photosynthetic life. And they would likely find other gases, such as methane and carbon dioxide, in concentrations that are also influenced by biological processes. The detection of these 4 elements, water, oxygen, methane, and CO2, all coexisting in significant quantities within the same planetary atmosphere, is something that would be very strange from a purely non-biological chemical perspective, because some of these gases, like oxygen and methane, tend to react with each other and destroy each other over geological timescales. Their sustained coexistence implies that there is a powerful, continuously operating system that is producing and replenishing them, a system that, on our planet, is life itself. Finding planets that are more and more similar to the Earth, and then meticulously studying their atmospheres in a dedicated search for these crucial biomarkers, are key objectives in the ambitious missions that will be developed and launched by the major space agencies in the forthcoming years. With its magnificent mirror of 6.5 meters, the new James Webb Space Telescope is already demonstrating its power, about 100 times more potent than the Hubble Space Telescope in its light-gathering ability and infrared sensitivity. There has never been a telescope of these dimensions, optimized for infrared observation, placed in space before, which means that what it discovers, the new views of the cosmos it is providing, could fundamentally change our entire concept of the universe. Astronomers were waiting for the James Webb Space Telescope for many years, and it is proving to be our ideal machine to learn much more about exoplanets. And what's the reason for this? This telescope is the most sensitive instrument ever deployed in space to capture infrared light. For the study of exoplanets, we can actually do two crucial things with it. We can attempt to image some of the planets we already know, particularly larger, younger ones, and we can measure their spectra, allowing us to derive the chemical composition of their atmospheres. The European Space Agency also has its own dedicated telescopes in operation or advanced stages of planning. Cheops, for instance, is tasked with the mission of studying exoplanets that have already been discovered, refining our knowledge of their properties. As Willie Benz, the principal investigator of the Cheops telescope, aptly stated, "If you look for life, if you look for something, the first thing you need to know is where to look." Right. You need to know where to look, and therefore you want to have a list of objects which optimize your chances. So as you think to find what you're looking for, looking ahead, 2026 is a key date. In that year, the European Space Agency plans to launch the Plato mission. Michel Mayor and Stefan Udry, pioneers in the search for exoplanets, believe that Plato will be essential if we are to find a true twin planet for the Earth. Plato will have 24 cameras, which will analyze the light curves of over 200,000 stars in search of planetary transits. It will look at many stars at the same time, especially bright stars, across a great part of the sky, trying to look really for planets like the Earth orbiting stars that look like the Sun. Many of the planets that these space telescopes will discover in the forthcoming years must then be confirmed and further characterized from Earth, often using the radial velocity method to determine their masses. The effect of the Earth on the Sun, changing the velocity of the Sun, is a minuscule 9 centimeters per second. Achieving this level of precision is a new step forward in instrumental improvement. This new step is already in motion. At the Geneva Observatory, a spectrograph 10 times more powerful than previous ones, named Espresso, has been built and installed on the Very Large Telescope in Chile. The goal of this new project is to achieve a precision of 0.1 meters per second, or 10 centimeters per second. And this just opens the possibility to detect these kinds of planets, like the Earth, orbiting a star like the Sun. This effect is so small when it's due to small planets that astronomers have to build incredibly dedicated instruments, often putting them in a vacuum to eliminate changes of temperature or pressure, because a change of 1/100th of a degree or 1/100th of a millibar in pressure will already induce an effect that is 10 times bigger than the effect of the Earth on the Sun. So, scientists really have to push to the absolute limit the technology of these spectrographs. However, the greatest technological challenge that scientists are currently facing in ground-based astronomy is taking shape in the high desert of Chile. It is there, at the European Southern Observatory that a truly revolutionary instrument is being built, the Extremely Large Telescope, or ELT. In a few words, the ELT is going to be the biggest highway towards a new understanding of our universe. It will give us the opportunity to discover things that today we cannot even imagine. When its construction is completed, anticipated around 2024 or 2025, it will be the largest telescope in the world, with a primary mirror an astounding 39 meters in diameter. The ELT will gather up to 15 times more light than current large telescopes and will be able to distinguish objects with a resolution never previously achieved. Think about a big spotlight beam in a soccer field and put just 10 centimeters away from it a little LED light. The ELT aims to distinguish, to resolve, the light of this tiny LED from the glare of the big spotlight, but from a distance of 200 kilometers away. The true potential of the ELT will be its capacity for capturing images of exoplanets orbiting nearby stars. Now, it won't be an image in the sense that you will see continents and water and clouds. What we'll see is a point source of light. But by looking and actually seeing that point source directly, it gives us the possibility to take the light from that point source and split it up into its component rainbow colors. And if we can find evidence for molecules in the atmospheres of those planets, such as ozone and methane, then we will definitely be able to show, unequivocally, that life exists on those planets. The universe that we discover with the ELT may cause in us the same profound astonishment that Galileo felt when he looked through his simple telescope for the first time. If you look back at how our understanding of the universe has changed in just the last 30 years, it's hard to imagine how much more of an understanding we'll have in another 30 years. But many are confident that in that time frame, we will have characterized planets around other stars, and we will have found the evidence that life actually exists around those other stars. What we are learning in science, historically, is that when you discover something, it's often opening more questions, and we are facing more surprises than anticipated. The first planets that were detected were Jupiters very close to their stars, and we know that they cannot form there. Super-Earths don't exist in our solar system, so we had no idea that they could be so numerous. There is a huge diversity. So, that's for the habitat for the development of life. Among all this diversity and abundance of planets, shall we find another place like Earth where life has been able to arise? Personally, many scientists are very favorable to the idea that life, at least in microorganism form, exists on other planets with convenient conditions. But this is not science. The only way is to do measurements and to detect this kind of form of life. It will not be so easy to prove 100% sure that a planet has life on it. It will be kind of hard because you want traces that are only due to life and not due to natural phenomena. And this is hard. There are a lot of things we can imagine that are also produced by natural phenomena, and we will have to be sure to disentangle these. The feeling is that we will have to have several lines of evidence, not just one, because it is a big claim to make. On our planet, chemistry evolved for thousands of millions of years to form intelligent life, beings aware of themselves who consider their place in the universe and look for answers. If life is very common, then we will find it very soon because it's everywhere. If life is rare in the universe, then it will take a long time to find, because we will need to find the right planet to look at. And if life doesn't exist anywhere else in the universe, then we'll never really know, because not finding it will not be proof that it doesn't exist. Whether we are successful or not, the search for another Genesis, for another instance of life beyond the limits of our solar system, will have been worthwhile, if we do believe that there is a kind of a mandatory evolution towards the development of life. Then it should be everywhere. But of course, there's a competition between what we call convergence, the idea that because the laws of chemistry and physics are the same everywhere, the same evolution should take place. But there are also the contingencies, the random events that will help or destroy life from place to place. So it's a statistical, kind of big, chaotic process. And the outcome will be 0 or 1. Either it's very, very hard to have life, or it's everywhere. And many choose to believe in the everywhere. The search continues, a testament to the enduring human spirit that reaches for the stars, that yearns to understand its place in the vast, silent cosmos. Whether we find echoes of our own existence or confront an even more profound solitude, the journey itself transforms us, deepens our appreciation for the precious, fragile gift of life on this small blue world, and reminds us that in the grand cosmic play, the pursuit of knowledge, the dream of connection, is perhaps what makes us truly alive. The universe waits, patient and profound, and we, its curious children, continue to listen for its secrets, for the whispers of other worlds, for a reply to our oldest question.
What is life? Is it something that breathes, that moves, that simply exists? Or is it something far more elusive? If a strange microbe were staring at us from a Martian rock, would we even know it was alive? And if life thrived in the oceans beneath Europa's icy shell, or floated in Titan's methane skies, would we recognize it when we saw it? Close your eyes and imagine a tiny rock lying in the frozen silence of Antarctica, just another stone half buried in the windswept snowdrifts of Allen Hills. But this one came from another world. Roberta Score, a lab manager from NASA's Johnson Space Center, was out there in the white void when she found it. At first glance, it looked like any other meteorite, but when scientists brought it home, examined its chemistry, and matched its fingerprint to the Martian surface, it revealed its true origin, Mars. And inside this unassuming piece of ancient basalt, something even more profound, chain-like microscopic structures uncovered through electron microscopy features that resembled fossilized organisms on Earth. Had we perhaps discovered the first whisper of life beyond Earth, locked in stone and time? This single rock, ALH 84001, launched a storm of debate, speculation, and wonder. Scientists scrutinized every micron, every chemical clue. Were these structures evidence of Martian biology, or just geology playing tricks with our expectations? But the rock posed a deeper question, one still unanswered. If life is out there, would we even recognize it? To search for life in the cosmos, we must first ask what life truly is. How do we define it without knowing what it might look like elsewhere? What are the universal signatures of life, if such signatures even exist? Could life be simple, hidden in dust or ocean spray? Or could it be something far stranger than anything we've imagined? In this journey, we'll explore how scientists define life not just as something that eats or moves or reproduces, but as a self-organizing information-storing system capable of reaction, replication, and adaptation. We'll venture from the chemistry of DNA to the lost seas of early Mars, from the cryogenic lakes of Titan to the boiling vents of Europa's abyss, asking again and again, is this where life begins? In December 1984, a small rock resting on the ice fields of Antarctica was picked up by Roberta Score, a field manager from NASA's Johnson Space Center. To the untrained eye, it was an unremarkable find. But ALH 84001, as it was cataloged, would soon become one of the most controversial meteorites in history. Initially identified as a meteorite, its chemical composition later revealed something far more astonishing. It originated from Mars. This Martian exile had been launched into space millions of years earlier by a powerful impact event and had journeyed silently through the solar system before crashing into Earth and resting undisturbed in the icy plains. After its retrieval, scientists conducted intensive studies, and nearly a decade later, a team led by physicist David S. McKay made a startling announcement. Under electron microscopy, they observed chain-like microstructures embedded within the rock features they argued could not be explained by abiotic chemistry alone. These, they proposed, were fossilized remains of Martian microorganisms. The world took notice. NASA's announcement made global headlines. Even President Bill Clinton addressed the nation, framing the discovery as a potential turning point in human understanding of life in the universe. But as the excitement cooled, scrutiny intensified. Other scientists pointed out that such microstructures could be formed by purely chemical processes without any biological involvement. The claim that ALH 84001 harbored Martian life began to fracture under the weight of peer review and alternative explanations. Yet even amid doubt, ALH 84001 continues to serve as a profound reminder of a deeper question. Even if alien life stood before us, would we be able to recognize it? The challenge of identifying extraterrestrial life begins with the challenge of defining life itself. To date, scientific literature offers over 200 definitions, but most of these can be distilled into a core framework grounded in three essential characteristics. First, life must possess the ability to store information. This means encoding details about its internal state structure and function in a stable medium. Second, life must catalyze chemical reactions. It must interact with and respond to its environment, acquiring energy, building complexity, and adapting to changes. Third, life must be able to replicate, producing copies of itself that preserve its structure and functions across generations. The renowned physicist Erwin Schrödinger was among the first to articulate these principles from a physical perspective. He understood that the transmission and preservation of information lay at the heart of life's persistence. From information comes reaction, and from reaction comes replication. These processes together enable what we observe as living systems that move, metabolize, respond, evolve, and above all endure. A more concise but profound definition was proposed later. Life is that which undergoes Darwinian evolution. It is the capacity for change through selective pressure and inherited variation that allows life to adapt and thrive across a range of conditions. On Earth, we see this manifest in all known biological systems. Our own biochemistry hinges on DNA for information storage, RNA for information transfer, and proteins as functional catalysts. DNA stores our genetic code. RNA interprets that code, and proteins carry out the essential reactions of metabolism and structure building. Importantly, these molecules participate in feedback loops. DNA can instruct the creation of proteins that replicate DNA itself. This elegant cycle is the molecular heart of terrestrial life. But when we seek life beyond Earth, we are faced with the daunting question, must alien life mirror this same molecular choreography? If not, how will we recognize it? Even within Earth's biosphere, we encounter ambiguous cases. Take viruses, for instance. They contain genetic material and reproduce, but only within a host. They catalyze reactions, but only passively. Are they truly alive? Then there is abiogenesis, the emergence of life from non-life. At some point on early Earth, chemistry gave way to biology, yet the boundary between the two is neither sharp nor well understood. It is highly likely that early life lacked the full DNA, RNA, protein triad. One leading hypothesis suggests that RNA alone may have been the first self-replicating molecule, giving rise to the so-called RNA world. Such primitive systems would be almost unrecognizable to us today, and yet they would meet the minimal criteria for life. They would evolve, they would interact, they would replicate. To better understand what extraterrestrial life might look like, we must consider the physical and chemical environments in which life is likely to emerge. Solvents are a critical piece of this puzzle. Life, as we know it, relies on a solvent to host biochemical reactions, dissolve nutrients, and mediate transport. On Earth, that solvent is liquid water. Water has several remarkable properties. It is chemically stable, capable of forming hydrogen bonds, effective at dissolving a wide range of compounds, and maintains its liquid state over a broad temperature range. Early life on Earth almost certainly relied on liquid water, and perhaps more importantly on moderate temperatures that allowed water to remain in its liquid state. Though extremophiles exist, organisms that thrive in boiling vents or acidic lakes, the origins of life likely occurred in more temperate, chemically stable environments. Moreover, early life utilized the same elemental building blocks that persist today: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon in particular is a superstar of molecular versatility, capable of forming stable and complex molecular structures essential for information storage and catalysis. The upshot is that early life on Earth, while primitive, was not entirely alien to us. It emerged under familiar conditions using familiar chemistry. Thus, it is reasonable, though not guaranteed, to hypothesize that life elsewhere in the universe may follow similar patterns. This hypothesis brings us back to Mars. Billions of years ago, Mars had liquid water on its surface, a thicker atmosphere, and a temperate climate. If life ever began there, it might have been carbon-based, water-dependent, and similar enough to Earth life for us to detect. And this is what made ALH 84001 so compelling. It could have been a glimpse into an ancient shared biological heritage. However, beyond Mars, the story grows more exotic. The icy moons of the outer solar system offer new and alien laboratories in which life might exist. Europa and Enceladus both harbor subsurface oceans beneath thick crusts of ice. These oceans are kept liquid not by sunlight, but by tidal heating from their host planets. Here in total darkness, life might rely not on photosynthesis, but on chemosynthesis, drawing energy from the heat and chemicals emitted by hydrothermal vents. Could microbial life thrive in these subsurface oceans, feeding on dissolved nutrients? Could evolution produce more complex organisms, perhaps eyeless creatures navigating by touch and echo, suspended in an alien sea? Titan, Saturn's largest moon, presents an even more bizarre possibility. Its frigid surface is dotted with lakes and rivers, not of water, but of liquid methane and ethane. At 180 degrees Celsius, water is as hard as rock. But methane is fluid and could, in theory, act as a solvent for a radically different form of life. Could chemical reactions proceed in such an environment? Could life emerge with membranes, metabolism, and replication, but without the warm, aqueous chemistry of Earth? The search for life in such places pushes our definitions to their limits, but even more extreme possibilities beckon. Might life exist that is silicon-based instead of carbon-based? Might it use ammonia, sulfuric acid, or even supercritical carbon dioxide as a solvent? Could quantum systems or unknown forms of matter support a form of existence that fulfills the criteria of life without resembling anything we currently understand? These possibilities remain speculative. Our only confirmed example of life is terrestrial. But as we begin to explore these questions, our first step must be disciplined. We must begin with what we know. Thus, in the search for the earliest life in the universe, we ground ourselves in the strictest definition. Life that uses water as a solvent exists within a reasonable thermal range and is based on carbon and its associated biochemistry. This definition serves as a foundation. It is the model by which we design instruments, craft experiments, and interpret data. From Mars rovers to Europa landers, from Titan probes to telescopes peering into exoplanet atmospheres, we begin by searching for the familiar. And with time, if we are fortunate, we may one day uncover the unfamiliar. But even then, we will ask, does it store information? Does it catalyze reactions? Does it replicate? If the answer is yes, we may finally say we are not alone. How to make life from cosmic dust to conscious beings. In the spring of 1952, in a laboratory at the University of Chicago, graduate student Stanley Miller initiated an experiment that would mark a watershed moment in the scientific search for life's origins. Working under the guidance of Nobel laureate Harold Urey Miller, designed a deceptively simple apparatus to simulate the atmospheric conditions of the early Earth. Into a sealed flask, he placed water to represent ancient oceans and filled the remaining volume with a gas mixture composed of methane, ammonia, and hydrogen molecules presumed abundant on the prebiotic planet. A continuous electrical spark arced through the chamber, standing in for the lightning strikes that would have been common in Earth's volatile primordial skies. At first, nothing seemed to happen. But after a few days, the water took on a faint pink hue. After a week, the mixture had turned a deep crimson. When Miller analyzed the contents using paper chromatography, he discovered something extraordinary. The liquid contained a suite of organic compounds, specifically amino acids, the very building blocks of proteins and by extension of life. Miller's experiment delivered a powerful message to the scientific community under the right conditions. Simple inorganic molecules can spontaneously give rise to the precursors of living systems: glycine, alanine, aspartic acid. These were not mere curiosities. They were biochemical fundamentals synthesized from scratch in a glass vessel with nothing more than water, common gases, and a source of energy. The implication was profound. If the chemistry of life could emerge in a lab, perhaps it had also emerged in the ancient pools of a young Earth. What made the experiment even more compelling was its elemental simplicity. The gases used, methane, ammonia, and hydrogen, are among the most common in the universe, composed of the basic building blocks of matter: carbon, hydrogen, nitrogen, and oxygen. These molecules are widespread throughout planetary atmospheres, comets, and interstellar clouds. That such ordinary constituents could yield such complex outputs hinted at a remarkable possibility. Life might not be a singular fluke of Earth, but a natural consequence of universal chemistry. Subsequent analysis of the original experiment's sealed vials revealed that Miller had synthesized even more amino acids than he initially detected, including some not commonly used in terrestrial biology. This raised another tantalizing prospect. The biochemistry of Earth may represent just one solution among many. Life constrained by evolutionary path dependence had settled on 20 primary amino acids, but chemically the potential permutations are far more diverse. The Miller-Urey experiment illuminated a key step in the transition from chemistry to biology, but it was only one piece in a much larger puzzle. To trace the origin of life, we must identify where the right ingredients, environmental conditions, and timescales converge. This raises the central question, where else in the universe could such a recipe be fulfilled? The Earth, of course, is our only confirmed data point. Our planet is awash in liquid water, bathed in sunlight, and shielded by a thick but balanced atmosphere. Critically, Earth orbits within the so-called habitable zone of the Sun, a circumstellar region where temperatures are suitable for liquid water to exist on a planet's surface. Move closer to the star and water vaporizes. Move farther away and it freezes. For life as we know it, liquid water is non-negotiable. Every star possesses its own habitable zone, the location of which depends on the star's mass and luminosity. For smaller stars, the zone is compact and hugs the star tightly. For massive luminous stars, the zone stretches far into space. In our solar system, the habitable zone stretches from just inside the orbit of Venus to just beyond that of Mars. Yet only Earth hosts persistent surface water today. Venus, once perhaps Earth-like, underwent a runaway greenhouse effect. The increasing luminosity of the aging sun triggered the evaporation of its oceans, loading the atmosphere with water vapor and driving up surface temperatures. The result was catastrophic: an atmosphere choked with carbon dioxide and a surface hot enough to melt lead. Mars, conversely, suffered a slower fate. Geological evidence indicates that Mars once had a thicker atmosphere and flowing water rivers, lakes, and perhaps even oceans, but the planet's small size sealed its doom, with a weak gravitational grip and a rapidly cooling core. Mars lost its magnetic field early in its history. Without this shield, the solar winds stripped away its atmosphere, and the water eventually froze or sublimated Mars, dried out and fell silent. These cautionary tales underscore how delicate the balance is. Being in the habitable zone is not sufficient. Planetary mass magnetic fields, geological activity, and atmospheric composition all play decisive roles. Even galaxies have habitable zones. Too close to the galactic center, and radiation from supernovae sterilizes everything. Too far out, and heavy elements become scarce, hindering planet formation. But even in the most promising environments within a star's habitable zone, on a geologically active world, with water life cannot arise without the essential ingredients, organic molecules. This returns us to the question of where those molecules originate. Earth may have begun with water, but not all of it was available at the surface. Much of the early water became chemically bound in the planet's interior or was lost during its molten phase. One prevailing theory holds that water and organics were delivered via impacts from icy comets and carbonaceous asteroids. These celestial messengers, formed in the cold outer regions of the solar system, retained volatile compounds and organics, which they deposited on young Earth during the so-called late heavy bombardment. This idea gained powerful support in 2014 with Japan's Hayabusa 2 mission to the asteroid Ryugu. The spacecraft retrieved dust samples and returned them to Earth. Laboratory analysis revealed a host of organic molecules, including several amino acids. These compounds had survived for over 45 billion years in deep space, shielded from harsh radiation. Their presence implies that the chemistry necessary for life was seeded across the solar system long before Earth's oceans even formed. Other lines of evidence reach further still. In 2003, astronomers detected glycine, the simplest amino acid in giant molecular clouds. These vast reservoirs of gas and dust are the birthplaces of stars and planetary systems. Spectral signatures of complex organics have been identified not only in our galaxy, but in others, even in the light of distant quasars. These findings suggest that the molecular precursors of life are not just widespread, but ancient. The cosmos was cooking organics long before our sun ever shone. The origin of these molecules, in turn, is rooted in the life cycles of stars. The periodic table is a stellar artifact. In 1957, astrophysicists Margaret and Geoffrey Burbage, William Fowler and Fred Hoyle published a landmark paper describing stellar nucleosynthesis. Stars through nuclear fusion forge elements from hydrogen. Our sun is currently fusing hydrogen into helium. Larger stars go further, fusing helium into carbon, oxygen, nitrogen, and beyond up to iron. When massive stars reach the end of their lives, they explode as supernovae, scattering their enriched cores into space. These explosions also forge heavier elements like nickel and cobalt. But the heaviest elements, gold, platinum, uranium, require even more extreme conditions. It is now understood that the collision of neutron stars with their immense gravitational and nuclear densities can generate the perfect environment to produce these rare elements. The universe, in other words, must be thoroughly recycled by successive generations of stars before life can begin. The Big Bang produced only hydrogen, helium, and traces of lithium. It was not until the first stars formed hundreds of millions of years later that heavier elements began to appear. Life in any form must therefore wait for at least one generation of stars to live and die. Planets rich in carbon, nitrogen, oxygen, and phosphorus only emerge after stellar alchemy has run its course. And only then, in the presence of water and suitable environmental conditions, can amino acids, sugars, and lipids begin to form. Life as we know it is not only rare in its complexity, it is rare in its preconditions. It depends on billions of years of astrophysical preparation, a precise orchestration of heat chemistry, timing, and stability. It is a story not just of biochemistry, but of cosmochemistry, of stars, planets, comets, clouds, and collisions. The Miller-Urey experiment demonstrated the plausibility of this alchemy under the right conditions, but the cosmic laboratory is vaster and older than any earthbound flask. To find the earliest possible emergence of life, we must therefore look not just to Earth-like planets in habitable zones, but also to the distribution of the raw ingredients, organic compounds, water, and heavy elements. We must track the chemistry of the universe backward through time, through stellar generations, through galactic cycles, all the way to the first molecules that ever formed. And eventually, to reach the ultimate origin, we must peer into the era before the first stars were born, into the dark ages of the universe when only hydrogen and helium drifted silently through the void, awaiting their moment to ignite and begin the long transformation from light to life. The earliest possible life. Let us imagine a future moment when humanity finally cracks one of the greatest mysteries of the cosmos. After decades of relentless investigation, theoretical models, experimental efforts, and technological innovation, the elusive identity of dark matter is revealed, not through myth or metaphor, but through the clean, precise lens of particle physics. A single stable particle, previously unknown, emerges as the solution. It interacts only gravitationally and occasionally through the weak nuclear force. The standard model of physics is updated detectors confirm its presence, and laboratories that once buzzed with dark matter pursuits fall quiet. The intellectual fire dims, proposals dry up, and the world of physics turns its focus elsewhere. But not everyone moves on. A quiet circle of researchers, driven not by consensus but by anomaly, remains unsatisfied. There is still a persistent signal, an excess of gamma-ray radiation flowing from the center of the Milky Way. For decades, it was dismissed as noise or as a byproduct of mundane interactions. But now, with the dark matter particle confirmed, the anomaly lingers unexplained. Driven by curiosity and the allure of unfinished business, these scientists pool what little funding they can, building a high-resolution gamma-ray telescope aimed squarely at the heart of our galaxy. And there it is, the expected glow of dark matter annihilation, predictable, consistent. Except for one detail, the signal is not steady. Subtle, almost imperceptible fluctuations emerge. The signal breathes. Minute changes in intensity repeat with maddening irregularity. The team works tirelessly, formulating and discarding theory after theory. Eventually, the funding expires. Disillusioned, the group disbands. Yet one researcher, a former graduate student, cannot let it go. On a restless night, she reopens the archived data and looks again. A new filter, a new method, a fresh eye, and then something unmistakable. A rhythmic pattern hidden in the noise. Every few seconds, the gamma ray intensity shifts up, then down, precisely like a binary signal. It continues, repeats, pauses, then resumes again after a month. And suddenly she begins to write, marking each increase as a 1, each decrease as a 0. The question is no longer about dark matter alone. It becomes something infinitely greater as the universe speaking. To answer such a question, we must first ask, what is life? What is its minimum requirement, and when could it have first emerged? Traditionally, life is defined as a system that can store information, interact with its environment, and most importantly, replicate itself. These are the foundational pillars of Darwinian evolution. On Earth, this triad is fulfilled by the interplay of DNA, RNA, proteins, and the dynamic chemistry of carbon-based molecules bathed in liquid water. But such a framework depends on a specific environment, a rocky planet orbiting a stable star with surface temperatures suitable for liquid water and access to a rich supply of elements like carbon, hydrogen, nitrogen, and phosphorus. When then could such a system first have arisen in the universe? We know that the universe began in a blaze of radiation and plasma nearly 138 billion years ago. For the first several 100,000 years, no atoms could form. The universe was too hot, too dense. Only after roughly 380,000 years did the cosmos cool enough for neutral hydrogen to emerge. But even then, there were no stars, no planets, only a featureless expanse of cooling gas and dark matter. The first star's massive, short-lived beacons, composed only of hydrogen and helium, ignited perhaps 100 million years after the Big Bang. These early stars lived briefly, exploding in titanic supernovae that enriched their surroundings with heavier elements, carbon, oxygen, nitrogen, the chemical seeds of biology. And so began the cosmic cycle of stellar death and rebirth. With each generation, the interstellar medium became more chemically complex. It is only after several rounds of such recycling that enough raw material accumulated to allow for the formation of rocky planets. If the timeline holds, then the earliest plausible moment for Earth-like life to arise, life built on carbon, driven by water, and capable of Darwinian evolution, must have occurred somewhere between 100 and 500 million years after the universe's birth. The Earth itself came far later, forming around 46 billion years ago, which means the first life in the cosmos almost certainly predates our own planet. But this still reflects only the biochemistry that we know. What of the chemistry we have not yet imagined? Astrobiologists have long speculated on alternative biochemistries. Water with its polarity and thermal properties may be ideal for Earth life, but it is not the only conceivable solvent. Methane, ammonia, hydrogen sulfide, and even liquid hydrogen fluoride have been proposed. Phosphorus might be replaced by arsenic. Carbon might yield its role to silicon, which also forms long molecular chains. Each substitution brings constraints but also possibilities. In 2007, physicist Vadim Sidovich showed that dust grains in plasma could, under the right conditions, self-organize into complex spiral structures. These are not living things, but they hint that matter, even in the most minimal and non-biological forms, has an innate capacity for order. Yet even these exotic life forms depend on chemistry, and chemistry requires atoms, which in turn require stars. No matter how alien all forms of life conceived so far must await the forging of elements in stellar furnaces. If we seek to push the origin of life even earlier, we must look beyond conventional matter. Theoretical physicist Frank Drake once speculated that life could form in the interior crust of neutron stars. These objects, the ultra-dense remnants of massive stars, possess unique states of matter, nuclear pasta, that exist nowhere else in the universe. Here, atomic nuclei are crushed into bizarre shapes, held together by the strong nuclear force. In such an environment, structures might self-organize, interact, and replicate, driven by the star's intense heat. It is speculation, yes, but within the bounds of known physics. Others have proposed more abstract entities, magnetic monopoles, strung together by cosmic strings forming networks capable of evolution. Yet the very existence of such particles remains unproven. And crucially, such exotic matter still requires energy and structure, conditions provided only by the emergence of stars. And so we arrive at the most radical possibility: life in the dark sector. Over 95% of the universe's mass energy content lies in the form of dark matter and dark energy entities that do not interact with light and remain for now invisible to our instruments. While dark matter is typically modeled as simple and inert, it is possible that it may host complex interactions of its own. There could be multiple species of dark matter particles governed by dark forces capable of forming dark atoms and dark molecules. If so, then a parallel form of chemistry utterly alien to us may exist in the shadows of the universe. If dark matter possesses structure, interactions, and internal energy, then it might also possess evolution. And if evolution is possible, then so too is life. Such life would not depend on stars. It might draw energy from interactions unknown to us. It might have emerged in the very first moments of the universe, long before the first photon of light escaped into the cosmic microwave background. It might still exist now, floating invisibly between galaxies, brushing past our detectors without ever triggering a signal. And perhaps, just perhaps, it is trying to communicate. Perhaps those gamma-ray signals dismissed as noise were structured emissions from intelligences forged in the dark. But such ideas remain speculative. To find the earliest possible life, we must return to what we can constrain. The universe did not produce the first stars until roughly 100 million years after the Big Bang. Only then could heavy elements begin to form. Only then could planetary systems, rocky surfaces, atmospheres, and oceans emerge. Even under the most generous conditions, life as we know it could not have arisen before this threshold. And even if more exotic forms of life emerged earlier, we may never have the means to detect them. The question then becomes not just when life first arose, but whether we will ever know that it did. Information from those ancient epochs is scarce. Time has stretched and faded the signals. The cosmos has expanded, and with it, the evidence has cooled and dimmed. If a civilization rose and fell billions of years before the Earth formed, leaving behind only faint traces encoded in gamma rays or gravitational waves, would we recognize them? Would we understand? Perhaps life began in the shadows, passed through fire, and emerged, blinking into the light. Or perhaps it danced in the dark, unseen and eternal, whispering across the void. The first life may not have looked like us, thought like us, or even existed in the matter we know, but life in all its possible forms has one thing in common: it leaves patterns. And if we are to find it, we must learn how to read them. Where is everybody? On a warm summer afternoon in 1950, the renowned physicist Enrico Fermi found himself immersed in a seemingly casual lunchtime conversation with colleagues at Los Alamos. The subject, as it often does among those who contemplate the fundamental nature of the universe, had drifted toward the prospect of extraterrestrial life. They speculated freely, throwing around ideas about the abundance of stars, the likelihood of Earth-like planets, the evolution of intelligent beings, and whether any of them might have visited us. The discussion moved on as conversations do, until Fermi, who had been silent for some time, abruptly posed a simple yet disarming question: where is everybody? This inquiry, deceptively innocent in tone, belied its profound implications. It is a question that has since reverberated through the decades as the central premise of what is now called the Fermi Paradox, a contradiction between high probability and conspicuous absence. Given the vastness of the cosmos, the abundance of potentially habitable worlds, and the immensity of time available for life to arise, why have we seen no evidence of alien civilizations? The paradox challenges our assumptions about the prevalence of life, the evolution of intelligence, and the nature of cosmic communication. The chain of reasoning begins with Earth itself. Our planet is not special in any fundamental sense. It is a rocky world orbiting a main sequence star, bathing in the warmth of a stable energy source, replete with water, carbon-based molecules, and a relatively benign atmosphere. It possesses a dynamic geology, a magnetic field, and a thin yet protective layer of atmosphere factors that together allowed life to gain a foothold, and through the crucible of evolution eventually produce intelligence. But these features are not unique. In fact, our Milky Way galaxy contains an estimated 100 billion stars, and recent observations suggest that as many as 5 billion of them may host Earth-like planets within their habitable zones regions where temperatures permit liquid water to exist on the surface. And this is merely one galaxy among possibly 2 trillion others within the observable universe. Moreover, the principle of mediocrity in physics, the idea that the Earth does not occupy a privileged position, suggests that the conditions for life, while complex, are not unique to our planet. Nature rarely performs singular acts. If a phenomenon is allowed by the laws of physics, and if there is sufficient time and space for it to occur, then it is almost guaranteed to happen more than once. Life, by this logic, should be common, and given the age of the universe, 8 billion years, there has been ample time for life not only to emerge, but to evolve into intelligent forms, capable of technology and communication. Indeed, life on Earth appeared as soon as conditions allowed. Geological evidence places the first microbial life at roughly 38 billion years ago, shortly after the Earth's surface cooled and oceans formed. The process of abiogenesis, whereby inanimate matter gave rise to self-replicating chemical systems, was not instantaneous, but nor did it require billions of years. Life appears to have arisen with remarkable haste, given the planet's violent infancy. This swiftness implies that once the right ingredients are present, life is not only possible, but perhaps inevitable. If this is true elsewhere, then by now the galaxy should be teeming with civilizations. Many of them would have had hundreds of millions, even billions of years of head start on us. Even at modest technological rates, such civilizations could feasibly colonize an entire galaxy within a few million years, a blink in cosmological terms. With self-replicating probes, interstellar travel becomes not a fantasy, but an engineering problem. Civilizations could communicate across light years using radio or laser signals. Artifacts of their presence, whether intentional or accidental, should be detectable. The solar system ought to be littered with evidence, alien probes, megastructures, chemical anomalies, or encoded transmissions drifting in the radio sky. Yet we find nothing. No signals, no probes, no artifacts, no signs of alien technology past or present. Not even biosignatures in the atmospheres of distant exoplanets. This is the silence that Fermi found so perplexing. The sheer absence of evidence is not merely disappointing, it is statistically improbable under the assumption that life is common and intelligence a frequent byproduct. Several explanations have been proposed to resolve this dissonance. The first is perhaps the most sobering, that life itself is extraordinarily rare. The path from chemistry to biology may require a precise sequence of events and environmental parameters so exacting that even among billions of planets, only a handful, perhaps only one, manage to navigate it successfully. Perhaps the emergence of life demands not only water and organics, but a confluence of tectonic activity, magnetic shielding, climatic stability, and countless other factors still poorly understood. If so, Earth may be a statistical outlier, a cosmic accident. Alternatively, life may be common but intelligence rare. Evolution does not favor complexity unless it provides a survival advantage. Microbial life dominates Earth's history and biomass. Intelligence, on the other hand, has arisen only once in 4 billion years. It is not clear that cognition of our kind is a convergent evolutionary strategy. Perhaps the development of tool-use language, abstract thought, and technological capability is the exception rather than the rule. Countless alien biospheres may thrive beneath alien suns, but their inhabitants may lack the desire or the capacity to contemplate the stars. Yet another possibility is that intelligence often arises but seldom endures. Civilizations may emerge, rise to brilliance, and then collapse. The threats are many. Ecological collapse, nuclear self-destruction, runaway artificial intelligence, pandemics, or perhaps even cosmic events like gamma-ray bursts. Technological sophistication may carry within it the seeds of extinction. If civilizations tend to destroy themselves before achieving interstellar reach, the galaxy may be a vast cemetery of dreams, worlds where intelligence once bloomed but left behind no lasting mark. It is also conceivable that we are simply not looking correctly. The methods we use to search listening for radio signals, scanning for atmospheric anomalies, hunting for Dyson spheres may be inadequate or misguided. Alien civilizations may use modes of communication or technology so advanced or so different from ours that we fail to recognize them. Just as an ant cannot comprehend a quantum computer, we may lack the sensory or intellectual apparatus to detect alien activity. Our assumptions may be anthropocentric, blinding us to more subtle or exotic indicators. Some have proposed that intelligent civilizations actively avoid contact, a concept known as the zoo hypothesis, suggesting that Earth is being deliberately shielded or ignored by a galactic community. Others speculate that we are alone, not because life is rare, but because we are the first cosmic pioneers in a young and expanding universe. If intelligence takes billions of years to emerge, perhaps humanity represents the beginning rather than the middle of a galactic story. Meanwhile, searches continue. SETI, the search for extraterrestrial intelligence, scours the sky for radio signals with artificial fingerprints. Infrared telescopes hunt for signs of waste heat from alien megastructures. Spectroscopic studies of exoplanet atmospheres look for biosignatures, gases like oxygen, methane, or ozone that cannot be explained by geology alone. Missions to Mars, Europa, Enceladus, and Titan seek microbial life beneath the ice in salty plumes or hydrocarbon lakes. Every discovery sharpens our understanding, but the silence remains. Still, the paradox endures. The more we learn about the universe, the more likely it seems that life should exist beyond Earth. Yet, with each failed search, the mystery deepens. Perhaps in time we will find that the cosmos teems with life and that our isolation is only temporary. Or perhaps we will confirm that we are truly alone, an extraordinary exception in an otherwise lifeless void. But if we are alone, then the implications are profound. It would mean that intelligence is not merely rare, it is sacred. that our responsibility as the sole conscious observers of the cosmos is immense. We would be the keepers of memory, the only eyes through which the universe contemplates itself. And if we are not alone, if someday we detect a faint signal, intercept a relic probe, or decode a message carved into the stars, then the paradox will finally yield. We will no longer ask, "Where is everybody?" but instead, what will we say to them? Perhaps one day, far in the future, our descendants will voyage among the stars and uncover the tombs of ancient civilizations, dead worlds, derelict machines, forgotten archives, whispering tales of triumph and tragedy. Perhaps they will discover that we were not the first nor the last to ask the question, that others too once looked to the sky and wondered. That in the dark, somewhere beyond the light of our sun, a monument still waits to be found, a distant Göbekli Tepe of alien origin left behind by minds that once dreamed. And in that discovery, we may find not just answers about others, but something essential about ourselves.